Hi, and welcome to my presentation about building compose hot reload. I want to be quick with the introduction. My name is Seb. I work as an engineer at JetBrains and on all things related to Kotlin since 2020. And today I want to talk about building compose hot reload. And I would like to take you on the same journey that I've been on for the last few months, which was building compose hot reload. And I think this journey can be separated into different chapters. First chapter will be about an accidental idea, and we will talk about how the JVM loads classes. We'll discover class loaders, have a short high, and maybe a little hangover. We'll discover the land of milk and honey, which is the JetBrains runtime, and we will talk about why this JVM is so special. We will have two boss fights. First, we need to fight the compose runtime, and then we need to fight the Kotlin and the compose compiler and convince both that hot reload is something that is actually a good idea and they should emit bytecode that is reloadable. So why should you care about hot reload? Now, if you talk about building UIs and compose is just a UI framework, the experience you have building UIs is basically the experience you have with your fast feedback loop cycle, basically writing code here and then visually checking it with your own eyes on the right side. So the faster this happens, the better it is, and this is the feedback cycle or the feedback loop. And of course, you can always just restart your application and check whether or not your code is okay. But I started my career as an Android developer, and I've been there and I've done that. I remember countless times going through the login screen over and over again just to check whether or not my change on the settings screens make any sense. There are some people that really enjoy automating this and creating some kind of UI or screenshot tests. Really good tool for ensuring quality, of course, because not only allows it to check in or test your code, but it makes sure that it also is not broken later on when you change some other things. Compose has this really cool feature called previews. It allows you to annotate your composable function, your widget, and the IDE will just render what your code will look like next to your code, which is super handy and a super nice tool. And other ecosystems, typically they also offer one more thing, which is hot reloading or hot swapping code while running the app. So you start the app, you do your changes on the code, and then it gets just reflected on the live application. You don't need to restart. But we have been effectively told that this is impossible to build for Kotlin and Compose, and it's only possible, quotes, for simple languages like JavaScript. And we had this mind just in our thought. Obviously, the talk is called Building Compose Hot Reload, and that means like there is a way to build it. And here's a demo I want to give you. We open the Kotlin Conf app from this year, and we navigate to the speaker screen. We search for steps, and maybe I don't like being just one of many steps, so we can change that. We could try to go straight to the speaker screen and intercept where we render these cards. And if Seb is in the name, and if it's actually me, we can then return just Seb. Otherwise, it's some other Seb. And if there's no Seb in the name, we can just use the original name. And once we check that in, we should see that it immediately reloads, and we are still on the speaker screen. We still have the filter applied, and we can do more and more things on the running application. So this is the thing we want to build. And here are our goals when we want to build this. So first of all, we want to build something that allows iterating on real-life projects quickly. We want to allow that almost all code changes are allowed. That means adding functions, removing functions, changing function signatures, adding a class, removing a class. Basically, everything that you would like to do, it should just support it. But the kicker is, we need to work within a really tight complexity budget. It doesn't help if we find some solution that we probably can't maintain and you don't like setting up. So we need to find something really simple, tight complexity budget. Now, where to start? And quite frankly, nobody wanted to build Compose Hot Reload. It was just a happy little accident because I'm still part of the Kotlin team. And at this time, when I started, the team, me included, discarded hot reload as being just not possible to implement or not feasible. And I just wanted to create a YouTube video about class loaders. And I thought hard about how I want to visualize a concept like class loaders, about like how JVMs do the class loading. And if you want to visualize such a concept, you need to come up with ideas how to put it in a video. So I thought, how about me just loading dynamic UI code with Compose, then swapping that out, and therefore I could explain this whole idea of class loaders with me just using Compose. Now, once I realized what that means, I was dumb enough to post this message in our Kotlin Slack team channel, where I said that it's easily doable to build stateful hot reload. Yeah, I learned my lesson. But this is the demo I posted in that channel. And it took me one Saturday to build this thing. And we will see the hello world version of Compose, a button remembers how often you pressed it, and the hello world for hot reload just goes one step further. It changes the look and feel of the button, and it also changes the behavior. And how awesome is this? This is like one Saturday of work. That's why I was naive enough to say it's probably easy to build. And I would have left it like that. Just a fancy demo in our team channel, and that's it, me bragging. If not for this message from Mikhail, our lead language designer. And I want to emphasize that sometimes these little messages that you get just in some random Slack channel, they have this huge impact on people. He said, I truly believe this works, deserves further development and productization. And then I felt entitled enough to just spend my entire time on that without even asking any managers. Sorry, Simon. Now let's get started. How can we build like this demo that I showed with class loaders? Obviously, you need to get an understanding of class loaders first. Now, as application developers, we don't often think too much about how our code is actually loaded into the runtime. But it is not just there globally. It will be loaded in some kind of namespace. And class loaders, they are such a namespace. And that means we can practically load the same class multiple times, and such class loaders being completely separated from each other. We could even go as far as loading two entire applications into the same JVM and have them run inside this one container then. Last important thing for us to understand is class loaders, they have a parent-child relationship, meaning that childs can typically access the classes from the parent, but not vice versa. Here are the class loaders that we need to understand. First one, that one is the least interesting one for us. The first class loader, the root of all evil, is the bootstrap class loader. It contains just internal classes to the JVM, and you as an application developer don't care. Me as a framework developer wouldn't care. So let's just skip on. It's internal things to people that build runtimes. But the next most interesting thing is the platform class loader. It contains all the classes that you are familiar with from Java as a platform. It contains Java lang string, Java lang boolean, Java lang thread. You get the point. Everything you know and love from Java, it's loaded there platform-wide for you. And then the most interesting class loader is what's called the system class loader. And this is typically, for most simpler apps, where all the code that you have for your application lives, it's available system-wide. That's why it's called the system class loader. So everything you compiled, all of your libraries, typically everything you pass with the java-cp-class path command. Now, how can we build hot reload or something that looks like hot reload when we look at this class loader? We might be able to say that, hey, there are clearly some classes in there that are part of my UI, and then there are classes that are clearly not part of my UI. I would say main screen, login screen, that looks like part of the UI, but the database and the Compose framework is not part of my UI. Now, we could think of just ripping that out and have a system class loader that does not contain anything that is related to our UI. And what happens then is we could load those classes that we think are part of the UI into something that we can create dynamically, and we call it UI class loader. We can call it whatever we want to call it. I just chose the name UI class loader. Now, if we ask our build tools nicely enough to continuously recompile when we do our changes, they will spit out new versions of those class files. And we could just dynamically load those new versions and use those new versions to render the next frame, right? And that would lead to the fancy demos and the prototype that I showed in the Kotlin Slack team channel. But we need to ask ourselves one question. Can we really build hot reload with class loaders? And is this solution really simple enough? And everything in life has trade-offs, and so do class loaders. They have a lot of power, but the power is really expensive in terms of complexity. And one thing that I would like to complain about is what I call them getting frameworky. That means, like, I just talked to you about some classes being clearly part of the UI, But who says what is part of the UI and what is not part of the UI? And with an approach like this, with class loaders, you as the application developer, you would need to do this. You would need to use something like a common UI source set where you refactor your code base and split everything that is part of the UI into this source set and compile it separately. And that kind of implies there will be some framework that you have to learn as well, and you need to learn its rules and pitfalls. Now, next thing I want to complain about is class loaders. They offer many traps to fall into, and some of them clearly explain my obsession with them. But my favorite one is something like this. Class foo cannot be cast to class foo. And I remember when I first got this kind of error, was something about an Android Gradle plugin and Kotlin Gradle plugin not communicating to each other. And I thought to myself, what the... but it's like, if you remember what class loaders do, it's clear for us now to understand what this issue is. They are namespaces, and it might be that the left-hand side here was loaded with previous UI class loader, right-hand side was maybe loaded in the new namespace that we just created. It's not the same class anymore, it's loaded in those namespaces, therefore they are incompatible, you can't just cast between them. So let's recap. We started with an idea, I would say. We started with the idea that the UI is just a function that can be applied to your application, and we can swap out that function, right? That's kind of the idea we had here. And I would say, yes, you can model this, but not in real life, because I would say UI code, it can launch side effects. It can store or remember state across the invocation of your one composable function. And quite frankly, it can have arbitrary interactions with the rest of your app. And that means every time something leaks out of this pure function, you're in trouble land. Now, let's recap again. Class loaders, they led to these fancy demos. But is it a good technology? Can we really build hot reload with class loaders? And is the solution simple enough? Let's recap. A user would need to isolate the UI code. A user would need to learn one more framework and all its pitfalls. A user would need to be aware of lower level JVM concepts. And if you think about this, I would say the first one is already a deal breaker. Because let's say you are an application developer, and we as JetBrains, the Kotlin team, we already ask you to separate your code into JVM main, Android main, iOS main, common main, whatsoever. Imagine us asking you to now also split all the UI code from not the UI code. It's kind of getting too much. Like, it's a stretch. We couldn't ask you to do this. User also should really not learn one more framework. It's already complicated enough. You have to learn Gradle, Xcode, Android, iOS, maybe the web. So many things on your plate already when you want to get started, and learning one more framework with special rules that you need to stick to, also kind of not acceptable. And the last point is more like, it feels wrong, maybe it would have been acceptable, but if we think about you having to think about lower level JVM concepts like class loaders, that would mean that you have to think about this in your common code where you write your UI. And now suddenly you write your common code and constantly have to think about how the JVM would behave if you write this code in a certain way. And that's kind of not ideal as well. So can we really build hot reload with class loaders? The answer is no, and that's kind of not good, because that effectively means game over, like the idea is done. But we at JetBrains, we communicate to each other, and obviously I was in touch with the Compose team at JetBrains, and it was Nikita Lipsky who just casually pointed me to this weird-looking project called DCVM. And it is a paper published in 2011, which talks about unrestricted and safe dynamic code evolution for Java. It's, I think, 11 or 18 pages. It's really nice to read. I highly recommend it. But what it talks about is that the JVM could be such a nice and wonderful platform to reload code in a really safe way. Only problem is nobody actually implements that except a JetBrains runtime, which is not just one part of the JetBrains runtime that happens to be implemented by accident. It's the first thing they advertise in the README. And when I say like they, us as a company, like fits us pretty well, right, to have the JetBrains runtime being this. Now, how does the JetBrains runtime actually allow for reloading code? Remember, we talked about a system class, or all the classes you have in your application. And to explain how the JetBrains runtime reloads code, we have this simple example where we just have two classes. One is called bar, one is called foo. Foo has a property x, right? Now, let's say we want to reload the code. And now we have a foo, or version of foo, which now suddenly has a new property called y. Now, what JetBrains runtime will do is, it will load the entire code into what's called a side universe. It's similar to, it is a namespace similar to how class loaders would be a namespace, but it's lower level. It's not accessible for you, but it's accessible for the JetBrains runtime. So it loads everything into side universe, complete isolation. It does some validation. It doesn't allow you to check in arbitrary things. It needs to be valid bytecode. It needs to stick to some rules. It validates the code. Then it migrates all the objects that you have in your running application to the side universe. Then obviously we need to reset the JIT state. If you had some code that some optimizing compiler already translated into machine code, and you change that code, that means the machine code is not valid, so we should drop that machine code and start JITting fresh. Now once the compiled state here dropped, we can just promote the side universe, and what was previously the system class loader tick for our side universe is just a regular system class loader. And we as application developers, we would have not noticed, and that means hot reload is done. Now I talked about object migration. I said it as if it would be possible, but let's think about it. How can we add a property to a class that has maybe already existing objects? The problem is, if you look at our heap, you might see that the JVM has stored all of those instances like next to each other in this continuous heap where there's an object header, the first property, the next object header property, and so on and so forth. And what we'll notice is there is no leftover space where we could put a new property y for all of our existing objects. So that means we kind of need to allocate more space and move the objects there. But that also means that all of the memory addresses of all of those objects will change, right? And is there a solution or some way where we could change the memory location of objects without breaking the entire application? And there is. That's what a garbage collector does. A garbage collector is allowed to allocate more memory and move objects around. And here's how the JetBrains runtime garbage collector does this when it reloads code. First of all, obviously, we need to allocate new memory for those new instances, which now has enough space to put two properties. Then it's as simple as copying the previous fields into their new memory locations. We see that here. Now we have to ask ourselves what to do with this property y, because we can't just reuse or re-invoke the constructor that either is not possible or it would break everything. So JetBrains runtime decided to just go with the JVM defaults being null, 0, and false. That means we kind of entered the land of milk and honey, right? We have this magical runtime. If we now would again ask our build tool, nicely enough, Gradle or Amper, to continuously recompile our code when we change it, we could take that code and scramble it up and have this one magical call into the JetBrains runtime, which does all the heavy lifting for us, just redefine classes. Now I want to show you, live how a version of hot reload would work with this. So let's open Compose Hot Reload. This is the repository where I'm actually developing Compose Hot Reload. And I checked out a special branch, which does not do more than just calling into this DCVM. Obviously, we can launch a sample app that is also inside this repository. And we can see that there is here this button we can increment. It's the hello world of hot reloading. So what we can try first is, instead of saying hello from widgets, we could say hello Kotlin conf, press Command S, and you can imagine how excited I must have been seeing that this now is showing up on screen. And if you have not seen it, we obviously can just make it a little bit bigger. And that is cool. But I told you that usually when you start working with hot reload, you then change look and feel of this button and its behavior. So let's go to the code that renders this inc here, and we just call it deck instead. And I was equally surprised to figure out that this doesn't show up. Like, it doesn't change. Now, probably it's just the source file that doesn't get reloaded, I thought, so I probably can just swap this, and now I expect nothing to, like, it should still increase. But if I press the button, it decreases. So it reloaded the logic here, but it didn't reload the text of this button. Now let's try to see if we can change, like, the title of this sample app also doesn't show up. Okay, we see that it changes inside this some widget magically work for whatever reason. So let's try to build up UI in there. We can use or create a new button on click, And I want to manage your expectation. When I hit Command S in a moment, I was also pretty frustrated to see a no such method error happening, because what the hell? So let's go back to the presentation. And where have I put my clicker? Ah, here. So what happened, and where has Awesome land? We have been promised that there's milk and honey, but turns out real-life frameworks are just too complex to only swap out function bodies and hope for the best. I mean, just because you reload the code does not mean that Compose magically reruns it and re-renders it, right? And also we need to think about what happens to state that was stored by Compose after you reload the code. And to understand this, we need to enter our first boss fight. We need to understand Compose and make it work in our way. And to do this, we need to learn how Compose actually remembers its state. And the first concept we need to understand here, we can explain by looking at this simple composable function. The first concept is called compose groups. Everything that you as a developer would call a scope is associated or has a corresponding compose group. And we can just render or draw in these groups. Every of those composable groups, they will be identified by one number. Now, when we want to store state, there's something used that is called a slot table. And it doesn't matter what kind of data structure it's actually, but we can think of it as a simplification, as a linked list or an infinite array. Important thing here is this data structure is just linear. Now, what happens if Compose wants to actually run this code? Let's say Compose wants to execute the app function. So we will have an active index into our table where we store our state. And the first thing that Compose will do is it will write into the slot table that it now enters this group 7091. Next thing it will do is it will store the mutable state into the slot table. Then it sees that we move into the next group. It notes down that we're entering this group now, entering the next group. And now the next interesting thing here, we also store some instances of lambdas, so on and so forth. Now if you look at this slot table, obviously after reloading code, the structure of this slot table is highly coupled to the structure of the code you had. And that means after reloading code, these sections might be entirely incompatible with the new code, right? And that kind of means that those sections need to be invalidated. And that poses a huge problem. How can we know which of those groups or scopes has actually changed and now need to be invalidated? Entering what we call the bytecode analysis part of Compose hot reload. And to understand this, we will look at this simple example here. It's again just like a very simple composable function app, has one scope. And the interesting thing here is there's a padding function, which is a utility function returning 16 dp. Now, we talked about system class orders. We can again just think of this being a very simple app with 3 classes in our system class order, foo, bar, and app. Now, every time your application wants to actually load such class, the Compose hot reload could hook into the JetBrains runtime, and before the JetBrains runtime even loads the code, we can look through this code. And we'll feed it through a component called bytecode analysis. This means, first, when we receive the bytecode of a certain class, which is supposed to be loaded now, we first put it through a Lexa tokenizer, and we will build Compose-aware bytecode tokens. Basically, some constructs of bytecode, they have semantics in Compose, like starting a group, ending a group, and so on and so forth. So we have this Compose-aware tokens. Then we feed that through a parser, which will give us a tree representation of your code. Why is it a tree? Because you in your code, you can have arbitrary control flow. And to model your control flow, we can represent this as a tree that we parse. And the important things here is that each of those scopes, we were able to figure out what associated group value this is. This is this group, and then the integer. We were also able to assign a hash value to this scope. And you can think of it as a simplification of this hash value being the hash of the bytecode inside the scope. It's not actually the hash of the bytecode inside the scope. I'm happy to talk about this later. But as a simplification, every time you would change the code, this hash value would change, and we would know that something inside the scope was actively marked as dirty, or should be marked as dirty. Also, every time when we see some scope calling out into another function, like invoke static, invoke dynamic, whatever happens, we just track this down. And this is what the arrow to padding function here does. We know that this particular scope depends on this padding function by calling it. Now we do this consistently. And we feed this into a component called the runtime tracker, and it will always have the most up-to-date version and information about your runtime available. It contains all the classes, it knows what was loaded, how this code relates to Compose, and what dependencies it has. Now what happens if we would like to change our code? Now we want to return or make the padding bigger from 16 dp to 32 dps. We will take the new version of your class, this app class, and feed it through the entire pipeline once more. And what comes out is very similar to what the JetBrains runtime called the side universe. Now this is like this runtime info tick, a new version of your runtime info with your change. On the left hand, we have runtime info without your change. And just to provide context again, we're still trying to solve the problem of figuring out what we should tell Compose to invalidate and what to re-render. Now, in order to figure out what to invalidate, we have a component which is called the invalidation resolver. Now we feed both runtime info tick into this invalidation resolver, and we can look at this tree representation of your code. On the left hand, without your change, on the right hand, with your change. And maybe it might not be super easy for us to spot immediately, but computers can do it immediately or pretty fast. The padding function's hash value change. That means there's a change in padding, meaning we can just mark this padding function as 30. Now the last thing that we have to do is we follow the dependency graph backwards, and everything that depended on this padding function is supposed to be marked as 30 as well. Now, I want to, once again, show you how a version of Compose hot reload would look like with this change. Therefore, we switch branch. Run the app again. And now we can try to see if the changes that previously did not work will now be reflected. So we change the title to Kotlin conf, press Command S, and yeah, quite lucky for us, actually updated. That means that somebody told Compose to drop the state there and re-render it. We can do the same thing for the increment button and check if this now works, calling it deck. And that's nice and dandy, but I think sometimes it's the best way of understanding a system is actually just debugging it. Let me start the same app by attaching a debugger. And we will set a breakpoint right in the core of hot reload, and we will see what's going on there. Now we have this app here loaded. Let's again change the title where we know where the change would be. I press Command S. We see the breakpoint hitting. It's in the middle of trying to figure out what it should tell Compose to invalidate. And what is cool about this is that we should now see that we have exactly the entities that I've told you about. We have something that's called previous runtime. We have a new runtime, and we have one invalidation, which kind of would be what I would expect. And if we look at this invalidation, it's kind of cool. It says there's one runtime scope info that is 30, and it's inside appkt.app, like the function app, which is exactly where we changed the code. And what is also cool is we see the concepts that I've been talking about here as well. There is this notion of method dependencies. There's this notion of field dependencies. It knows about children scopes, and also it has here this associated hash value. But of course, like we can still try to see if we are there yet, and if Compose hot reload is finished with this change. Therefore, I might want to just give me a clean plate where I can just start building out stuff. And we can test whether or not we can still break Compose hot reload. Spoiler, we can. So we do a card. We might want to have a button with an on-click, and the button might just say hello world. And that's cool. We can click this button. But so far, it's not like that interesting. We need to have a state. So we do a counter by remember, mutable state, state mutable, okay, state of 0. Option enter, press Command S. Still pretty cool for us. Then we do a counter. We ignore the underscore. Yeah, it renders. So far, it seems good. Now, the last remaining thing is we need to wire up this counter, right? We need to increment it. And I want to temper your expectation. I press Command S now. And I know that this will be unsatisfying, but if we press this, we will again see no such method. Though. That's, like, imagine how I must have felt at that situation. Now, let's run it again, because it's not even the only issue I found. I want to focus on the second one. What I also found is me switching from using a card to a surface here, and I press Command S to reload the code in this version of hot reload. It renders the entire application red, and it's super scary. It says like unsupported operation exception. Somebody added function 2, somebody removed the function interface, function 3. So that sounds strange. So let me go back to the presentation and ask the question, who the heck changed my super type? So we focus on the second issue I found. And we need now to enter our second boss fight. We need to convince the Kotlin and the Compose compiler to actually emit bytecode which we can actually reload. And to understand the problem I've shown with this card and surface issue, I've come up with this really simple-looking UI, which is like just a stack of cards nested in each other, and they render this A, B, and C text. The interesting part, however, lies in the build output. It does not only emit our class, like sum widget, but it also has these utility classes that it emits. Composable singletons, sum widget, lambda1, lambda2, lambda3. So obviously we should look into what's going on there. And I don't expect you to read this. The interesting things are, this is what's called the lambda1, and that's the thing that renders C. Now, keep that in mind, because when we look at this, it's not clear why lambda1 would be the one that renders C. And here's what's happening in the Compose compiler. When a Compose compiler tries to transform your code, it wants to make sure that all of your Lambda instances are actually singletons. And therefore, it does a transformation straight in the IR of Kotlin, the intermediate representation inside the compiler. But it does this by going depth first. So the first thing it visited and finished visiting will just get transformed first. And therefore it says like, hey, let me grab a new fresh name. It's composable singletons, lambda1. Next thing I see is lambda2. Next thing I see is lambda3. And maybe you have already spotted why this will be a huge problem for reloading code. But here's an example, a simple example on breaking that. Let's just add one more nested thing, and we use a surface and use text D to render that. Now, if Compose wants to compile this, it will see the most inner thing first again, assigns it name lambda1, and now previously, we used card as lambda1, which was a function 3. Now it's a function 2, and already we have some kind of issues. But what is even worse, what was previously called lambda1 is now called lambda2. What was called lambda3 is now called, what was called lambda2 is now called lambda3. What was called lambda3 is now called lambda4, and so on and so forth. Entire thing just rotates. And it's not just that it rotates within this method. Your entire source file now emits classes with a name that just rotated by a little bit. So that's obviously not good. And we need to find a solution or a way on like emitting code that is actually reloadable. So here's how we can do this. Instead of emitting a class name that depends on the code that is inside this code, or is just using an incremental counter, we could just use a stable class name. And we already have a concept in Compose which gives us a stable integer number which is associated with a scope. This is what we previously introduced as Compose groups. They are associated with an ID, and this is pretty stable. So when Compose wants to build a class name for this lambda, you can think of this stable integer being created by us putting stuff into hash function. So we put into this hash function that we are in my package sum widget. That's the function we're in. Then we're in a stack of card calls. We are in a surface call, and then here's our function signature. This spits out a number which is stable. That's not the exact way that this number is actually calculated, but it's a way of thinking about it. It spits out a number, and we can just use this number to then use this as a class name. If we now do this for all of those lambdas, we will get something that is stable across us reloading the code. Now let's see if this actually leads, with these patches, if we can now actually fix the issue. So I switch back to live coding. And what we are supposed to do is go into the branch that has some compiler patches in there. And we can look into code that is pretty much what I've shown you previously. This is the stack of cards. Let's wait for the project to compile. and we see a stack of cards. And previously, without the compiler patches, we would expect that a simple change, like switching from card to surface, would entirely break hot reload and marks everything as red. In this case now, with the compiler patches, it emitting the class names differently, it now suddenly works. So we can freely switch between card and surface, and we are now free to just simplify this code here, and again say hello, press Command S, and see if it still works by us very simply switching from something that was previously function 2 to something that is now function 3. So let's get back to the presentation. We need to ask ourselves the same question as we did with class loaders. Were we able to build compose hot reload within the complexity budget? And I want to remind you how it started. We started with this accidental idea about using class loaders, and that meant that users had to kind of stick to a framework, refactor their code, make sure that all of the UI code is in a special place, compiled in isolation with the rest of their code. The user had to deal with issues like foo cannot be cast to class foo, and all of those things. And we found a solution in the end, which is as simple as you applying a Gradle plugin, pressing run in the IDE, and getting hot reload for free. So were we able to build compose hot reload? I would say we are almost there. And the way that we were able to build this is because the DCVM, you saw it, was like the paper was published in 2011, but so far you have not seen that many similar applications of it. And the reason why I think compose hot reload might be really enjoyable technology in the end is we were able to contribute throughout the entire stack. We were able to collaborate with the compose compiler team, with the Kotlin backend team. We were able to do some changes, like even tiny, but some small changes to the compose runtime. Obviously, we collaborate with the team at JetBrains that builds the JetBrains runtime. We know the folks that have all the build tooling. We collaborate with them, with Amper and Gradle. It took us a little bit of parsing and tracking of bytecode modifications, and we used the JetBrains runtime. So I think we kind of did it. And I would like to encourage you to try compose hot reload today. You can get started either by visiting github.com/JetBrains/compose hot reload, or you can visit our jetbrains.com/help, where it also talks about how to set up compose hot reload. Now I think that's it, and I'm open for some questions if you have any. Thank you very much.